Hello everyone. Today's lecture is going to be about predicting the properties of materials using supervised learning. And really, the core concept that I'm going to be wanting to express to you all today is what are representations and how do they make supervised learning on materials data possible. Before we get into that, let's start off to make sure that everyone has a good grounding in supervised learning. So supervised learning algorithms are designed to learn mappings. Mappings between some kind of inputs to a process and outputs. And this very broad definition can encompass many different flavors of the kinds of machine learning models that you'll see in the literature. They could be simple regression techniques, like this chart on the bottom right, or binary image classification models. But sometimes you can see things that are a bit more subtle, like this chart here, which shows a segmentation model, which is a subclass of the kinds of classification models that you see. But due to the fact that it isn't as easy to tell which are good segmentations and which are bad, unlike a simple binary yes or no, there's a lot of subtlety that goes into building these kind of models. And additionally, sometimes it's even harder to quickly identify where the inputs and outputs could be. For example, Google Maps recently switched over to using message passing neural networks to predicting traffic conditions. And here, the inputs very well could be the history of the time to complete a certain route on a map over the past several hours. Or it could be based on weather or time of day. There's a lot of kind of interesting questions that go into being able to take a scientific problem like image segmentation or traffic prediction and being able to cast them as a supervised learning problem. And that is really the refrain for being able to use supervised learning within materials science, that there's really some flexibility on inputs and outputs. It isn't always image to yes or no, or correlating two variables together. And one good example of this is considering the question of what does a sodium crystal look like, or sodium chloride crystal look like? And this could be the kind of prediction tasks that you could very well employ with machine learning, where I think it's a very good example for understanding what's difficult and how to go about machine learning and materials by examining the process that me, as someone with a background in inorganic chemistry, would tackle this problem. I would first consider that sodium and chlorine are separated by a very large electronegativity difference, which means it's going to be ionic bonding, and there will probably be a very large energy gap between the valence and conduction bands. And what this means in short is that there'll be minimal interaction with visible light and probably a clear material. Additionally, I know something about crystals, and I know that these two elements are similar in size when they're in their ionic states, which means that based on Pauline's rules, it'll have a coordination number of 6, which means cubic symmetry. So taking all of this together, I would infer correctly, and probably cheating in that I know that table salt forms little cubic crystals, that in fact sodium chloride forms cubes that are clear. And you may notice that there's a lot of logical reaches in being able to make this inference, such as knowing something about how sodium and chlorine act as individual elements, or knowing something about crystal chemistry and how that relates to forming different crystal structures. And this is something that really emphasizes why making predictions about materials properties is difficult for a computer. I can't just take the text NaCl and give it to a computer and have it be able to infer all these logical processes. But I can take sodium chlorine and define it in a way that makes it possible to express rules like the ones that are described here, that high electronegativity difference means clear, or similar atomic radii means cubes. And these are the kind of simple rules that it's possible for a machine learning algorithm to learn without a lot of data. And the real term that we use to describe this process of translating a kind of subtle type of data like a materials problem, or as in the camps of traffic prediction, the descriptions of what factors might include traffic, is called representation. And that is taking a type of data and defining it into the form needed by machine learning, which primarily algorithms take mathematical tensors of quantitative attributes. But the process goes on more between just simply converting data. I could convert sodium chloride into a numerical representation by taking a picture of NaCl with my phone and encoding that picture as a series of pixel values. That would be a horrific way of trying to learn the properties of sodium chloride or other minerals, but it is technically a representation. Now, one probably better example of a way you could approach this problem is illustrated by this picture on the left over here, where I've developed a cartoon of a model where I'm trying to learn which materials are ionic solids. And I could approach it by, say, ordering them by their fraction of sodium, which in this case could make a machine learning model. I can construct two decision rules that high or low sodium mean ionic, but that is not the way that ionic materials work. Rather, if I take these materials and order them by their difference in electronegativity, I could learn not only a simpler machine learning model, but one that is bound to generalize better because it is able to learn the underlying physics. And that is the process that we've illustrated here of coming up with a representation for a material. Now that's a simple problem, but it's very illustrative of the kinds of problems that we've seen often in the materials literature. And it's happened enough that the literature is abound with many different good kind of policies for how to create these representations. And the ones that I think are the most informative is described in papers by the group of Anatol von Lilienfeld and papers by Felix Faber, and I've given a reference to one of the early ones on the bottom of this slide, that sound like this. When I take a representation, it first must be complete. If I have different materials within my data set that are indeed different, they have to have different representations. Ideally, you also want these representations to be compact, that they don't carry features that are redundant for the problem. And they also must be descriptive, that the features that I do include group materials in intelligent ways. Like in the example that I just gave you with identifying ionic materials, I want things that say I group materials by the polarization of their bonds, a hallmark of whether a material is ionic or not. Another thing is I want these features to be simple. Really, they need to be fast to compute, so I don't want to use something necessarily like density functional theory to be able to describe a material if that's going to be too slow to the point that building the machine learning model is going to be arduous and running it is going to be too slow for the kinds of problems that I needed to solve. So if I take these four rules and go back to my lens if it is ionic, I could say that both of these pack the complete check. Neither produces overlapping points. They're both compact, they're each a single feature, but they're different in the fact that my difference in electronegativity representation is descriptive in the fact that it matches my textbook understanding of ionic materials, and of course both are equally simple. I can compute them both trivially, even by hand. So while I would say that problem solve, difference in electronegativity works for this problem, this can become more complicated. Like, what if I start to get materials that are not charged balanced? Those materials are not going to form ionic bonds because there's, say, an offset. I can't form, say, sodium 3 oxide and have it all equal a charge balance compound. So you can start to think that, okay, maybe this fact that I have a representation is actually more dependent on the kinds of data that I have, and there may not be a single one that works for every problem. And there you'd be right. We can take a look at this paper from 2014 from a group in Japan that tried to come up with a machine learning model to predict the melting temperatures of compounds. Now, in this particular case, they ended up using density functional theory as one of the inputs into their machine learning model, which I actually used as an example 2 slides ago of something you may not want to do. And here it works very well. They only wanted to screen a set of 100 compounds, and they chose properties available with density functional theory like volume per atom and bulk modulus that are relatively quick to compute. So they could do that for 100 materials, and this model is still remarkably useful to the community. I can predict a melting temperature without either having to synthesize the material or performing costly computations like doing a coexistence simulation, which can cost tens of thousands of processing hours compared to the 10 I would spend to calculate the bulk modulus. So really, when you're thinking about these representations, there is a lot of work that goes into deciding what it is about the problem that, one, can define my data set, but two, what do I actually care about the machine learning model and how does that tell me about what is acceptable for using as an input into a machine learning model and what isn't. And if I'm to kind of further try to muddy the waters, there are also different schools of thought on how one can build a machine learning representation. There are discriminative representations where I try to capture my intuition about the problem. So something like looking at elemental properties like differences in electronegativity to capture whether a material is ionic, or things like what is used in facial recognition, where I look at the distance between someone's pupils as a feature that describes different people or not. And these have the advantages of capturing a lot of the physics that goes into a problem. Ionic materials can be well described by bond polarization, therefore electronegativity, and people all have different faces. The size of their nose and the ratio between that and their eyes captures them very well. And one of the challenges, well, here I've got a typo, is the fact that it bakes biases into the model. And also, you have to have an understanding of the physics of the problem in order to be able to solve it in the first place. Now, a second way of thinking of making representations that has especially become popular with neural networks is thinking more descriptive. How can I create a representation that adequately distinguishes materials from each other in a way that's compact? So here I can describe materials by their atomic fractions, or say an image of a person just by the pixel values. And this has the advantage of being maximally expressive. Unlike a machine learning model that's limited to working with features that already reduce a rich concept like an atomic or a chemical compound into simple rules like difference in electronegativity, descriptive representations ensure that a machine learning model has access to all of the underlying raw data. And this may require more data to effectively train. I'm going from a raw representation, but as we've seen in the fact that facial recognition is now dominated by neural networks that use descriptive representations, it is possible to use these kind of techniques to create very effective models for the fact that they can access complicated rules that may have been unavailable if you had simply boiled down the problem to very simple features. Additionally, one other problem you'll find a lot in materials science is that there are often two different schools of thought in how I come up with descriptive representations in particular. There's one that I have a bias towards of using every feature I can think of in order to build a representation. Like, let's say if I was doing ionic materials, I'd also throw radius difference in there as well. Even though it doesn't necessarily match my understanding of the problem, the idea is that my machine learning model could still learn from this rich data, filter out the noise from the signal, and be able to find rules that I would not have expected to begin with. And in fact, this coming up with every feature you can think of is a good way to start if you don't necessarily understand the physics at all. And the problem is, and this is one that we're going to give you some real-life examples on, is that there's a danger of overfitting. Your machine learning model could discover patterns that aren't actually due to the physics in the data, but are perhaps due to some bias in the sampling. One really kind of difficult way that bias shows up in machine learning is if you look at the kind of models that have been considered for giving parole decisions, where factors like race or income can show up in the machine learning model as very important features, but they're only important features because there are societal factors such as racism that can lead towards kind of existing features within the data of whether people are reconvicted of a crime rather than things that are truly due to kind of the true factors driving a problem. In another case, there's also a school of thought that you could avoid this problem of coming up with improper relationships in your machine learning model by taking a very curated hand and identifying what kinds of features can go into the machine learning model in the first place to really inhibit from learning unphysical rules. Here, while this has the power of avoiding bias, it's also taken in its own risk of being able to limit the kinds of rules that your machine learning model can pick up to only the ones that you expect it to find. Another consideration to think about with developing representations is that different kinds of machine learning models actually mandate different kinds of approaches. One of the examples that you're going to learn in our next series of lectures are the kinds of approaches used for kernel ridge regression, which kernel ridge regression, if you're unfamiliar with it, works by learning pairwise similarities between different entries. So here the question is less of how do I come up with individual features that describe a machine learning model, but how can I come up with a kernel that can take two different pieces of data and be able to infer how they are similar to each other. And effectively, this can only come down to needing a single feature. Pardon another typo in my slides. Tools like random forest regression, on the other hand, work best with dozens or hundreds of features because they are built with the idea of having feature selection and random sampling of different facets of data into the construction of the algorithm itself. And there are also tools like neural networks, which we talked about with facial recognition in a previous slide, that are designed explicitly to automatically learn representations from data. As an example with my cartoon here, how I can take a graph that's sparsely populated with points and being able to gradually decorate it with information that's derived from that very simple input. And this is what neural networks do very well, so they work well with this kind of discriminative input data that allows it to learn these complex relationships. It also has the ability to work with variable number of features for inputs, which is something you can't do with random forest, different input shapes for different types, and really you're only limited by your creativity of what you can express within a neural network architecture. So you can end up working with kinds of input representations that are completely incompatible with things like kernel ridge regression or random forests, but are equally powerful. So that wraps up my lecture for today. And really the bits I want you to take away from this are a definition that representations are our way of encoding chemistry and physics into machine learning models, and that there are a couple different ways to think about developing these features, namely you want things that are complete, that they can adequately distinguish your data, but be able to describe the differences between those points in a simple way that captures the underlying physics and can be easily derived from computational methods. And the final point I really want to leave you with, and will hopefully reinforce through the next series of lectures on different representation for molecules, is that there is no best representation. The fact of how you choose one, or the motivation for choosing one, is strongly driven by what is the data you have on hand, what is the kind of ways you want to use this machine learning model, can you tolerate a long time to calculate a feature, or could you not? Or what is it the kind of machine learning algorithm that you're using? Is it a neural network? Is it a kernel-rich regression? And that's also going to drive your thinking about how you choose these representations. And my hope during the rest of our module is you'll be able to learn how to explain these differences, such as why would I use a different ridge regression representation for, a different representation for a ridge regression than a neural network? And what are the kinds of ones I choose for organic versus inorganic materials? And then finally, how can I identify when my choice of representation and algorithm has created a machine learning model that has bias in it that I don't want? So hopefully these will be the next couple things you're going to learn in the course and will be the subjects of our following lectures.